Today, I'll solve one numerical problem on continuity equation. Here is the problem statement. Oil flows through a pipe PQ with a diameter of 1.1 meter at a velocity of 4 meter per second and then continues through a pipe QR with a diameter of 1.3 meter. At point R, the pipe split branches RS has a diameter of 0.7 meter and carries 1/3 of flow from PQ. The flow velocity in branch RT is 3 meter per second. Find the volume rate of flow in PQ, the velocity in QR, the velocity in RS, and then the diameter of RT. So now here, suppose that from the if you read that problem, so here PQ diameter is given. So PQ diameter is 1.1 meter, that is given, and velocity is also given. So that is 4 meter per second. Now here the volumetric flow rate in PQ is Q1. At point R, so in that point R, okay, so QR, the diameter is, QR diameter is given, so that is 1.3 meter. So now here that is Q into QR, volumetric flow rate. At point R, the pipe split branches RS, so RS and then RT. So RS branch pipe diameter is 0.7 and carries 1/3 of flow from PQ. So that is 1/3 of Q1. The flow velocity branch RT, so flow velocity RT, that is 3 meter per second. Now we have to find out that volumetric flow rate PQ, velocity, what will be the velocity means V2, okay, and then velocity in RS, so what will be the velocity, so that we have to calculate, and then diameter of RT, so that is we have to calculate. Now here the data given, so D1 again, so that is 1.1 meter and V1 is 4 meter per second. D2 is given, that is 1.3 meter, diameter of branch pipe 1, so D3 is given 0.7, okay, and then flow rate is given, for that is Q is 1/3 by Q1 if that is Q1, and then V4 is given, so that is 3 meter per second, that is given. These are the data given. Now our objective is to determine the volumetric flow rate in PQ. So we have to find out that volumetric flow rate, then determine the velocity of QR, in that QR, that V2, what is the velocity, and then the velocity of RS, what will be the velocity of RS, and then diameter. These are the objective. Now, so what are the physics involved here? Continuity equation. The principle of conservation of mass states that the total discharge in the main pipe must be equal to the total discharge in the branch pipe. So means whatever mass comes in is equal to mass comes out. So whatever mass comes in here, okay, so that will be equal to mass comes in for this branch pipe plus this branch pipe. So mass comes in is equal to mass comes out. So that is actually the continuity equation. So here the continuity equation can be applied as follows. So Q is A1 into V1. So here Q is nothing but area, cross-sectional area of this PQ pipe into V1 is equal to that cross-sectional area of QR into V2 is equal to cross-sectional area into V3 plus cross-sectional area of F4 into V4. So that is Q is equal to A1 into V1 is equal to A2 V2 is equal to A3 V3 plus A4 V4. So A1, A2, A3, A4 are the cross-sectional area in the main pipe and second pipe, branch pipe 1 and branch pipe 2 respectively. And V1, V2, V3 and V4 are the velocities in the main pipe, second pipe, branch pipe 1 and branch pipe 2 respectively. Now first we know the diameter, so here diameters are given, so D1, D2 and D3. So now we have to calculate the cross-sectional area. So A1 is cross-sectional area A1, so that main pipe pi by 4 D1 square, so that is pi by 4 into 1.1 square, so that is 0.9503 meter square. A2 pi by 4 d2 square, so pi by 4 into 1.3 square, so that is 1.327 meter square. A3 pi by 4 into d3 square, so that is pi by 4 into 0.7 square, so that is 0.385 meter square. So that cross sectional area, as diameters are given, so we can easily find out the cross sectional areas. So cross sectional areas A1, A2 and A3. Now volumetric flow rate PQ. So volumetric flow rate PQ here. So cross sectional area into V1. So here cross sectional area into V1. So that cross sectional area is 0.9503 into that velocity is 4 meter per second. So that Q1 is 3.8012 meter cube per second. Now in QR is Q1 is equal to Q2, that is nothing but A2 into V2. So already we know volumetric flow rate Q1, that is Q2, so that is nothing but A2 into V2. From here we know the cross sectional area A2, so we can easily calculate V2. So already we know, so here that what will be the volumetric flow rate in this pipe is equal to this pipe. Now we know that volumetric flow rate this pipe, so that volumetric flow rate Q2 is nothing but that A2 into V2. So as that diameter is given, so we can easily calculate V2. So that V2 is calculating here. So V2 is nothing but 2.86 meter per second. Now velocity in RS. So 1/3 of Q1 is going through this RS. So Q1 we know. So that is 1 by 3 into 3.8012. So that is 1.267 meter cube per second. Now using the continuity equation, so QRS into A3 into V3. So A3 we know. So that is 0.385 and V3 we have easily calculated. So V3 is 3.29 meter per second. So we just plug the value and we can easily calculate V3. Now that RT diameter, we have to calculate diameter of RT, we have to calculate. So QRT is Q1 minus QRS, or you can that 2/3 by Q1, we can do that. So that Q1 minus QRS means Q1 is the inlet mass flow rate minus QRS. So rest of the mass is coming toward coming through this QRT pipe. So that is 3.8012 minus 1.267. So that is 2.534 meter cube per second. Now using the continuity equation, so QRT is equal to A4 into V4. So velocity is given here. So from here we can easily calculate A4. So QRT is equal to 2.534 and A4 we have to calculate, and velocity is given 3. So from here A4 is equal to 0.8447 meter square. Now we know that cross sectional area is nothing but pi by 4 d to the power d4 square. So from here, so we can calculate d4 is nothing but 1.04 meter. So now if I do the summary or final answer, so volume rate flow in PQ, that is 3.8012 meter cube per second. Velocity QR is 2.86 meter per second. Velocity in RS is 3.29 meter per second, and diameter of RT is 1.04. So here if I go back here, so diameter is 1.09. Okay, so and V3, so here 1.04. Velocity in RS 3.29 and velocity QR 2.86 and 3.8012 meter cube per second. So all this answer we can easily calculate by applying continuity equation. That's it for today's class. Thank you.